It is section 6.5, work done by a variable force. When an object moves a distance d by a constant force F, then the resulting work W must be force times distance. You know that? We'll use the knowledge for the computation of work done by a variable force along a line. Here we assume that the force is a continuous function of x, the object's position. And here we will find the work done by the force over the interval a to b. We'll use the same technique, partitioning, approximation, and Riemann sums and their limit. Okay, so we partition the interval a to b into n subintervals, and we choose ck, an arbitrary point from the kth subinterval. And now, because f is continuous, then in small subinterval, f will not vary much on the subinterval. So we may approximate the force by a constant evaluated at ck, fck, and distance. So that is approximated work on kth interval. We sum them to get on a Riemann sum, and as n approaches infinity or the partition length approaches 0, we can get the definite integral. Here now ck will become x and delta x become dx. So here we define the work, and for variable force fx moving an object along the x-axis from a to b, that is integral from a to b f of x dx. Okay, now we'll see this example. This example, the major purpose is just consider the units. The unit of the integral are joules if the f is in Newton and x is meters. So it's a Newton meters, that is same as joules. And if f is pounds and x is feet, then the result is foot pounds. Okay, so work done by force of f of x equal 1 over x squared newtons in moving the object along x-axis from 1 to 10 meters. That is now integral from 1 to 10, 1 over x squared dx. Antiderivative of this one is same as minus 1 over x, and evaluation from 1 to 10. So it becomes 0.9. The unit is joule. Okay. Here we have Hooke's law for springs. Now, Hooke's law says that the force required to hold or stretched or compress the spring x units from its natural length is proportional to x. So we say in this way, F is kx. K is now spring constant or force constant. And this Hooke's law is quite good, quite accurate when the force is relatively small so that it's not distort the metal. But there's no metal to become perfectly elastic. So the some portion is distorted. So if you try to stretch too much, then it'll be distorted. So it's a small force is working very nicely. Okay, example 6.37. Find the work required to compress a spring from its natural length of 1 foot. Okay, natural length 1 foot, and now to a length of 0.75 feet. Now the force constant is given here 16. That means that here the force is 16x. Now from 1 to 0.5, the difference is 0.25, 1/4. So that now it's quarter compressed. So the work will be integral from 0 to quarter, and force, that is 16x and dx. So that is now 8x squared, and from 0 to 1/4. So when x is a quarter, it is 1/16, so that is half. Of course, here now, foot-pounds is the unit. Now, let's see this example. A spring has a natural length of 1 meter and force 24 Newton holds the spring stretched to a total length of 1.8 meters. That means that now stretched length is 0.8 meters. So here force 24 is now K times, now the perturbation is 0.8. So from here we can get the spring constant, and 24 over 0.8, which is 30. That means that if you try to express a force, then force will be 30 and x. Right? You can get that. How much work? Of course, the required quantity is this one from part A. Okay. How much work will it take to stretch the spring 2 meters beyond its natural length? Okay. Now work is now beyond the natural length. That means that from 0 to 2, perturbation is from 0 to 2, and force is 30x. Okay. So that is now 15x squared from 0 to 2, which is now 60, of course, Newton meter. So that is joule. How far will 45 Newton force stretch the spring? Okay, that's 45, and we already know that the spring constant is 30, and then now the amount to be stretched is x. So from here now, we have x equal 1.5. That's the final answer. Okay. Now we have this example. We'll deal with some lifting objects and pumping liquid from containers. Okay, the bucket is now 5 kilograms. So here we have a 5 kilogram bucket. Is lifted from the ground into the air by pulling in 20 meters of rope, so that this height is 20 meters and at a constant speed. The rope weight here 0.08 kilogram per meter. How much work was spent lifting the bucket and rope together? Here we have to notice that kilogram is an SI unit of mass, so that if you want to get force, then you have to multiply gravity constant, mass times gravity constant, which is 9.8 meter per second squared. Okay. So that is now weight. The force is okay. Weight is a kind of a force. Okay. Now, so we have to get the work for the bucket and for the rope separately, and then we can add them. For bucket, here weight, so that it's a sort of now force. Weight is here 5 kilogram for bucket is 5 kilogram and times gravity constant, so that after multiplication it becomes 49 Newton. So work for bucket is now the force is now constant. So for constant force, it is now moved 20 meter, so that 49 Newton times 20 meter, which is 980, and Newton and meter, which is same as joule, right? Okay, 980 joule is the work for bucket. And here, now again, for rope, and work for rope, and we have to get weight, that is now force for rope. Here, the rope weighs 0.08 kilogram per meter, so that along with multiplication along the length, here that will be now the kilogram is mass. The reason we are multiplying this one is that in the beginning the length will be 20, but once it's lifted, so that once reach at x position, then the remaining length will be here 20 minus x, so that here the weight of the this mass of this loop will be here 0.08 times 20 minus x, right? Of course, x is moving from 0 to 20. That is mass, and times here gravity constant, so that along with these two, we can get this quantity times that one, 20 minus x, that is Newton, is not constant force. So that here, work for rope must be now integration from 0 to 20, and then here 0.784, and here that is 20 minus x and dx. Okay, so we can get this one quite easily. 0.784 is a constant, and now that is from 0 to 20, and x, okay, 20, not x. Okay, that is 20 minus x dx. By using the area, we can get the integral quite easily. Here, that is now 20 minus x is this straight line, 0 to 20. So the area of this one is the same as 200, right? 400 times divided by 2, which is 200. So that is same as 0.784 times 200. So that is 78.4 times 2, which is now 156.8 joule. So if you add this one and that one, then you'll get here now that amount, 1136.8 joule total. Okay, that's the end of the section and end of the chapter. Thank you.